Before we proceed to the second session, let us welcome Dr. Sreekanth VM to this FDP, online FDP. I would like to consider this as my privilege to introduce Dr. Sreekanth VM before you. Dr. Sreekanth VM, working as Assistant Professor in Department of Mechanical Engineering at Mamilla Engineering College, Kannur, Kerala. He has completed a Master of Engineering in Computer Design from Government Engineering College, Salem, and Anna University, Chennai. He completed a PhD entitled Design and Development of Custom Laparoscopic Surgical Tool Handle using Additive Manufacturing Technology from Coimbatore Institute of Technology, Coimbatore, under Anna University, Chennai. He has his research interests are in the domain of additive manufacturing, customization, ergonomics, and product development. He has published 5 research papers in various international journals, including SCI and Scopus. Moreover, he has got 12 years of experience in teaching as well as in the research domain, research area. With this brief introduction, I would like to welcome Dr. Sreekanth M P to deliver the session. Over to you, sir.
Yeah, thank you, Pradeep sir, and Lijo sir. Especially thanks to St. Joseph Palai and the Department of Mechanical Engineering for inviting me for the session. And good afternoon to all. My topic of presentation is actually additive manufacturing, possibilities of user-involved product development. So that's what my title I given. And obviously, I am actually sharing my experience during my research, as well as some recent developments or recent experience while doing project or while guiding the project for SJCET students. So I'll just share those experience, and I hopefully you all know that what actually additive manufacturing or maybe rapid prototyping, that was the first name for that technology, right? Then I will not detail those things. Actually, I will share my experience. I hope it will be useful for you. Any issues, sir? Yeah. Okay. So coming to the topic. So I hope all of you are from faculty and research arena, right? That these areas. So I think probably some of you maybe already finished your PhD, or some of you may be in the verge of finishing the PhD, or maybe some of you are actually starting the research, right? So I hope it will be, that means my experience will be in one way or the other will help you to continue your research. Okay. So this is my topic of discussion. That is, I will just go through what is actually additive manufacturing, then what is this FDM or FFF, and along with that, this polyjet technology. So these two technologies actually I worked for my research, and customization, ergonomics, and anthropometry. So these are actually needed while I am talking about my research. Okay, and some of the case studies from my side, as well as from some of the journals I collected, and that will also I present in a brief. Okay, so why I choose this FDM and FFF or this polyjet only for the topic of presentation, because I worked in that, and I am not going to present it for SLS, SLA, etc., because I didn't have any hands-on experience on that. Okay, so I will actually present you that, and hope you know that this series of technologies. There are actually these ASTM classified it into 7 series of technologies, 7 categories. Okay, and in that there are several technologies are there in that, but it is actually classified into 7. And the name actually came for this technology is actually rapid prototyping. Why? Because during that time, that is 1980s, actually this technology came into existence. At that time, this rapid prototyping is actually used for making the prototypes, because when they want to create a prototype for a particular product, or at the design stage, or maybe at the testing stage, at that time they need to go for the actual or the conventional way of manufacturing it or producing it. So that is actually more time consuming, and the cost is involved are more. So for that, actually, they developed this series of technologies to make the prototype fast, and they can test it, or maybe they can analyze it, or they can see how it will look like. So for those things, they can present to the management, or maybe the manufacturing team, or the within the design team. They can present it, and they can get a better feedback about that product. So that's what actually the starting of this rapid prototyping. And when the time goes, the names like solid freeform fabrication, digital manufacturing, rapid manufacturing, 3D printing, etc. was there. And at last, this ASTM, they came into they formed a committee, and they told that this series of technologies will be called as additive manufacturing. And 3D printing, that is normally the word we are came across through media, because additive manufacturing will not be, that means if you are talking to a common man, or common human being, that means they don't have that much technological knowledge in this, there should be a catchy word for that, right? So this media actually started using this 3D printing, and actually there was one 3D print, that means one technology was there, and I think that is developed by Massachusetts Institute of Technology and 3D Systems. That name is actually 3D printing. I will show you that. That is actually that binder jetting technology. It will come under binder jetting technology, and it is like our injection printing. Okay, so this inject printing. Okay, so this is actually the basic idea about that, and I hope you know that what is actually additive manufacturing is. You are depositing the layer of material, or one layer of material over the table, and you are adding the layer of material over the other. Okay, then you can make the prototype, or maybe some nowadays even final product, end use product also we are manufacturing it. So this is actually that way of printing or manufacturing the product layer by layer. Okay, so the layer thickness may be vary for different machines, or maybe different technologies. That depends on which technology we are using, or which machine we are using. So that will vary. Okay, so normally this rapid prototyping cycle will start from a CAD design, or CAD model, computer design model, that will convert to STL file. That is standard, that actually came from stereolithography. So first machine commercialized in additive manufacturing, but later it is actually called as standard tessellation language. Okay, tessellation means making triangles. So you are actually approximating the CAD model to a by connecting different triangles. That means number of triangles will be connected to approximate your project, your product, or your object. Okay, so from there you will go to pre-processing stage. So pre-processing normally involve the orientation, or maybe scaling, etc., and creating the support structure. Then after creating the support structure, orientation, by selecting the orientation and scaling, that you will transfer to the machine. Then you will click the button build or print depending on the software. Okay, then the machine will start the printing. So obviously at that time you no need to think about what actually machine is doing. Machine will do that. Just periodically checking is enough. Then post-processing, normally some of the many of these technologies need some post-processing stages. That's what actually removing the support structure, maybe increasing the surface finish, or maybe a secondary machining may be needed to do that, and maybe some painting, this type of things may be needed for getting a better visibility of that product. Okay, so this is the normal stages included in almost every additive manufacturing technologies. Hope I am able to I'm audible. So if anything is, please let me know. And one more thing, if you have any questions in between, obviously you can ask me. Okay, now, so as per I told you that ASTM International, so before it was known as American Society for Testing and Materials. So they actually formed a committee, that is F42, on AM technologies, additive manufacturing technologies. They classified this series of these machines, or this series of technologies, into 7. That is VAT photopolymerization. That is the classic example is stereolithography apparatus. So that will actually made by, that means in a vat or in a container, there will be a photopolymeric material will be there. By hitting the correct light, correct intensity light, maybe laser or maybe UV light, so you can probably normally you will using ultraviolet light, so you can cure this material. That means you can make that as a solid. So that is the specialty of this photopolymer materials. The second one is actually material jetting. So classic example is actually polyjet technology by Stratasys. There are Aiden object series are there for this type of technology, and this is actually the starting material is actually liquid. So that liquid will spray on the table. Okay, and UV light will be along with the nozzle, and that nozzle, that UV light will cure this material. Okay, then material extrusion, that is fused deposition modeling or fused filament fabrication. Both are coming under this material extrusion machine, and this is one of the lowest low cost machine we can. It is available. That is, we can easily afford these materials. Even 25,000 also it is available, I think. Then binder jetting. This I told you that 3D printing material is there. This technology was previously called as 3D printing itself. From there actually that name 3D printing came. So this is actually we are using, instead of a UV light, we are using a binder for gluing together this powder. So this is based on a powder technology, and metal can be printed by using this technology. And powder bed fusion. This is examples are selective laser sintering. Selective laser sintering and electron beam melting. In some cases we can use electron beam melting for this, and we will use powder for one layer of powder will be deposited on the table by using a laser, CO2 laser. Normally we will use carbon dioxide laser to cure this or fuse these machines, this powder together. Okay, then sheet lamination, that is laminated object manufacturing, is the example for that. And we will use a sheet of material we will deposit on the table, and that will be supplied by 2 rollers. Okay, then according to the CAD data, it will be cut from that sheet. That required object will be cut from that sheet and by using a laser. And directed energy deposition, that is example is electron beam melting is also there. Laser engineered net shaping, and that is laser engineered net shaping, etc. are the example for direct energy deposition. In this, actually we are using a powder material, but instead of laying on the table, this powder as well as the powder will come through a hooper, and it will come to the nearer to the nozzle, and that particular point, that laser or maybe the electron beam will be strike on this material, and this material as well as the laser or maybe electron beam will deposit it on the table together. Okay, so that's what it is called as directed energy deposition. Okay, the material will be directed and energy will come along with that to the table. So because of that, this powder will be that means powder will fused together to form the layer. Okay, so these are the 7 series of technologies according to ASTM International. Okay, and in that, actually I told you that I actually worked with FDM, fused deposition modeling, as well as polyjet technology. Okay, so in that FDM, fused deposition modeling, it is a solid based technology. That means the material in the initial form will be in a wire form. Okay, so that wire will come through a nozzle and into a heated chamber. So this will be normally in heated chamber. So what will happen is, at that time this material will become in a semi-solid state. Okay, like our toothpaste. For an example, you can think about toothpaste. So if you press at the back end, so what will happen? It will actually paste it on that wherever we are projecting it or directing it, right? So it is similar to that. So there will be one model material will be there. This green color is model material, and this is for support material. You can see that I hope you know that why we are using supports, because supports needed for extended part, or maybe you have to support that, right? So you just see that if you lay this model material, and till this there is a gap, actually for our object there is a gap. So what will happen if you didn't support that? So this part will fall down when you are projecting it. Why? Because this is in a semi-solid state. It will be in a semi-solid state during the operation. So the curing will fully complete it after completing all this process. And if you are taking out, so slightly it will be sticky. Then if you place it for some time, that will become fully perfect solid. Okay, so this will actually come through this nozzle. This is called as nozzle, and it can move in X and Y direction, and table will move in the Z direction. So normally at the initial stage, this top table will be at the top of the extreme top of the top position, and from there, this for one layer, after depositing the one layer, this table will move down for a next one layer. Okay, so in that case, in that way, actually this is working. Okay, hope it is clear. So this is actually about FDM. Okay, and I hope it will be better to show you a video of how this FDM is working. So is that okay, um, participants? So this is actually done when my project is yeah, okay, so
Yes, I
thank
can
you.
see. Yes.
Yeah, you thank you. So you can just, I will share this tab instead for that. So is it visible?
Yes,
um,
sir. Yes, yes.
yeah, okay, thank you. So this is the table, this one, and this is the nozzle, and the material will come from the bottom to the top. And you can see that here, you can see that this is actually that support material. This is actually an ABS material, acrylonitrile butadiene styrene, and this support material is also as same material but in a different composition. This is actually a chemically soluble material. So what will happen is, after finishing this operation, so you can just take this out and you can uh, deposit it in a hot water around 75 degrees Celsius hot water, and some COH chemical will be there, that will be supplied by Stratasys itself. Then you can put this material into that, and this brown color material, that is the support material, that will be solved in that. That will become that will be removed by solving that. It will soluble, it's a soluble, chemically soluble material, so that will be removed by using that. Actually there was some other support structures that is called as bars, breakaway support structures. So that is actually you have to remove by using some hammers or maybe some knife. You have to remove that. So at that time what will happen, if you are careless, what will happen, this material will actually damage the model material itself. So there is a possibility for that. That's what actually they invented this type of chemically soluble or hot water soluble support structures. So that is actually cleaning the nozzle tip. So after that it will deposit the material again. You can see here, this part is actually not, there is a slight gap is there. So that is actually not started till now. So in this way actually, so this operation will be actually done by the material. That means the machine will choose where it has to deposit the material first. Okay, so that depends on how that process is actually happening. And I already told you about pre-processing, right? Pre-processing, it will be something like this. So normally in the material, in the software, you can choose that. So this will be that build volume. Normally this will be called as build volume. So that means it depends on the machine. Okay, the build volume will be depend on the machine. It may be 250 by 250 by 120 or something like that. So you have to, that means if your model is big, you have to scale down that, and you have to fix in between. So if the material is beyond this size, obviously you can't print that. So you have to make the scaled one. So this is what normally happen in the pre-processing stage. And obviously it will depend on the software you are using. So but it will be similar operations will be there. So you can bring the STL file from your computer and you can bring that. So why it is showing that message is it's actually bigger than the build volume, because it is beyond the build volume for that particular machine. So that's what it is showing, that there is some error message will be coming. So you can set the position as well as the, so this is actually orienting. So this is called as orienting. So in any way you can orient the product. And if you are orienting in this way, the one main problem is actually staircasing effect. So if it is a cylindrical object, so a staircasing effect will be there, so that you have to reduce as much as possible. Okay, that means slightly that the edge will be not very smooth. So if you are actually concentrating on the smooth object or the extreme surface finished object, so it will be used in a better means in a another orientation to avoid that staircasing effect. And another one is if your size of the object, that means height of the object, if you are orienting in this way, so just think that this height is till this. Okay, so at that time, another problem for this FDM and similar additive manufacturing machines are, in the Z direction there is a problem of reduced strength. So that is also you can reduce by orienting it in a different way. Okay, but you have to that means you have to create your objectives. That means whether you need only a surface, that means you just want to show how the object will look like. So just a prototype, and you are not supposed to, you are not bothered about the strength. So you actually needed the extreme surface finished object. So at that time you can think about whatever it may be. So you can think about producing that object in the Z direction also, because normally we will say that in 3D printing or additive manufacturing. So if the height in that Z direction is more, so that will not be. If you are keen about the strength of the material or strength of the product, it will be better to orient in the other way. So don't go for Z direction height is maximum. Okay, so that you can reduce as minimum as possible. So that's one idea behind this. Okay, orienting the object in different way. So you can do that, and you can position it. So this is actually scale down. So you reduce the size of that object, then you scale down, then you position that in that extreme right position of that table. Then you can bring the other objects. So it came. So that means together you can. So that means if you are just need to make the prototype, you can bring all the. That means if you need actually 4 objects to be printed in this particular run, so you can bring all the 4 objects and you can scale down. So you just need to see that how it's look like. So you can do that, and you can position it accordingly. Then you can start the. So all these 3 objects actually came there. So now we have a wheel, hand wheel. So that wheel actually it's very big size. So we again reduce that and bring there. Okay, so you can position it accordingly. So scaling, orientation, positioning, everything can be done in the software itself. Okay, so this will be the position of that. So after that, after completing all these operations, you can just go for printing. So it will create that support structure also. You can generate the support structures. So normally every 3D printing machine or additive manufacturing machine, normally what it will do, normally it will lay a 5 to 10 layers, depends on the machine or maybe technology, 5 to 10 layers of support material will be there below the object. So when you are, so normally you will remove the products from the table by using a knife or a chisel type object. So at that time, it shouldn't damage our product, right? So for that, actually, we will deposit around 5 to 10 layers of, maybe more than that sometimes, layers of support structures below the object. Then only you can remove it easily without damaging your product. Okay, so this is the way normally creating this support structures as well as the positioning and orientation of the objects. So you can see that this is the actual support structures we generated. So this will actually below that, and because there is no much extended surface or extended parts in this object. So only that bottom support structures is enough to complete this particular product. Okay, so this is the way we normally do that. Okay, so hope you have the small idea about how it is actually working in this softwares. And obviously this with the change in machine as well as the software, slight variations will be there in the operation, but normally we will do this orientation, generating the support structures, scaling, positioning, etc. in the similar fashion, in the similar manner. Okay, so now so that is about this FDM or FFF. And why I called this FFF is FDM is actually that term, that fused deposition modeling, that is called as fused deposition modeling. This term is actually used by Stratasys. Other all manufacturers actually using FFF, that is actually called as fused filament fabrication. Okay, so that is because the technology is same, there is no difference in that, but this Stratasys actually patented this word, so others are actually using FFF, fused filament fabrication. Okay, sorry. So now another machine actually I worked with is actually polyjet process, polyjet technology. This is actually material jetting process. You can see that this is a nozzle. Okay, from this, can you see this cursor? Can you please tell me? So whatever I am showing here, is the cursor is visible?
Yes.
Yeah, okay, thank you. So because I can point at it easily. So this is actually that nozzle. So normally that liquid will be in a container, that material will be in a container, both support as well as model material. So I actually worked with an object 260 Connex, that machine. So there will be two compartments for materials. Two model materials as well as two support materials can be inserted in that together in that particular machine. And we can insert actually two different materials for model. That means model material can be two different materials possible together. Okay, because we can make the Stratasys. This is also a object 260 Connex is also a Stratasys product. So they are telling that if you are mixing these two materials, there are different materials they patented: Vero white, Vero blue, Tango plus, Tango black, etc. So this is Tango plus Tango. Tango family is actually a rubber-like material, and Vero family is a rigid material. Okay, so you can insert Vero white as well as Tango plus together in a at the same time you can insert or you can install that material into your machine, and you can print by mixing these two materials. That is 60% from Vero white, 40% from Tango plus. That is possible in polyjet, that is in object 260 Connex, that type of series of machines. And the specialty is you can change this composition, maybe 60-40 or maybe 70-30, etc. So that depends on that rigidity, and the flexibility will be according to your selection. Okay, and they called it as actually digital material. Okay, so they called it as digital material. So you can see that here, this is the support material, this white one, and the yellow one is the model material, and UV light will be there in these two sides. You can see that UV light is there. From there, what will happen is the material will come through this nozzle, and it is a nozzle actually, it will spray the material on the table. Okay, so that is a basic idea about this polyjet technology, and UV light will cure that material during the run. Okay, and you can in this object series machines, the specialty that you can print two materials together, because one product fully Vero white and another product fully Tango plus. That is actually possible in this type of machines. And obviously you can use these two separate materials in a same product. Okay, same product in different two sections. Actually, we have an experience that we printed a model of our brain. So left half will be in a different machine, and the right half will be in a different material. So, but we printed actually in together in one run. In single run, we actually printed both material in the same product, that is brain model of a brain. Okay, that was possible in this type of machines, but in FDM, that you print, that's what I worked, that is not possible. Okay, so you can see that these are some of the application areas of additive manufacturing in construction field. Okay, this is in Dubai and this is in China, and for medical applications like cranioplasty as well as the lower jaw implantation. And this is actually made by GE, General Electricals, for their one of the aeronautical engine. And this is a bionic eye. This is actually in under development. This is not fully developed. It is under process. And food industry as well as you can print customized chocolates as well as cakes by using this. Okay, so by using this type of machines, that means instead of our normal plastic material, Vero White or Vero Blue or maybe ABS, you are using a food material, a cake or maybe chocolate material, and that you will paste it through this. And the specialty is you can, by using the CAD data, you can make a customized cake or maybe a chocolate for one particular person. That was the idea behind it. And main advantages are it is fast process because it is actually reduce the time to market, because when you are in the design process, when starting from recognition of need to the marketing stage, or during that you can actually incorporate this prototyping stage in different way, right, or different stages. You can incorporate this prototyping process. You can create prototypes in different stages, and obviously if you are going for conventional process to make the prototype, obviously that will be more time consuming. But comparing to that, actually additive manufacturing is fast process. Another one is less wastage of material, because you are adding the material, you are not subtracting anything, because you know that in subtractive manufacturing like lathe and milling, shaping, etc., you are actually removing a lot of materials to get your final product, right? So here actually wastage of material is less, because only you are removing the support material, but the model material what you are creating is actually you are adding the material one over the other. And obviously the main advantage of additive manufacturing is customization. Why? Because this is actually we you know that this mass production actually started. You can they actually this mass production in mass production actually they think about one size fits all product. That means everybody will use the same product, same size, same shape, same thing, right? But if you want to create a customized product, that means obviously you know that some of the, just think that if you're going to buy a car, at that time they will show some series of color will be there, some extra fittings will be there, maybe that will be optional, right? So if you have money you can choose that, but that customization is actually limited there. But in additive manufacturing actually you can think about an individual customization product, because actually if you are going for individual customization only, this particular machine or this particular technology is feasible. Otherwise if you're mass production, actually I told you this is a very limited size of build volume is available for you. In that actually making a mass produced product, that will be very difficult for you. But when you are compared, normally our additive manufacturing will be compared with injection molding machines. So injection molding machine, obviously you know that when you are when you have a mold created, you can produce lot of n number of products from that, but the products will be similar, same shape, same size, right? But just think that there is an alteration, that you got some feedback from your customers, then you need to change one of the dimension from that, or maybe one of the object from that product to be redesigned. So if you are redesigning it, obviously you have to redesign your mold, right? Mold should be redesigned, then only you can print the altered or modified product from that injection molding process. But in this case, what is the advantage is you have a virtual model, right? A CAD model is there actually for you, right? So from that actually CAD model, the alteration is possible in infinite way, right? So you can change your dimensions, change your shape, change the shape, etc. can be done in n number of times. There is no problem with that, because if you buy that particular software, so that is the only investment from your company or your college. So after that, if you are using the product for 5 years or 10 years, there is no problem. Maybe you need to just renew the license, that's all. So if you bought that, so that is the only investment you have to put it in. But if you create an object or a product in that, you can change the dimension n number of times. There is nobody will go to ask you why you change that, right? You can keep on searching and keep on changing it, and if you until you are satisfied with the product, till that time you can do that, right? So just think that you launched a product for an individual by using Additive Manufacturing. So you created the CAD model, you printed it, and you supplied that. So after getting that product, that means he or she, that particular customer, giving you a feedback that, so this particular part is not comfortable for me while using it. So can you change it? So that's what the question coming from the customer. So you are actually designed for that particular customer, right? So at that time, you already have your CAD model. So you can change that shape or maybe the dimension of that particular part in your CAD model by using SolidWorks or maybe CATIA or maybe any other modeling software. You can change it. You can take printout again and you can supply that. But if it is an injection molding process, what will happen? You have to create the mold first. So the cost is more. But here, the changing that dimension will not be a big issue for you in the CAD environment. So that's what the advantage we got in CAD as well as additive manufacturing process. Okay, hope you understand that. So that is, individual customization is the main aim. It should be your aim for that. And very complicated shape, complex shape can be fabricated, and there is no need of tool and jig and fixtures, etc. Because if you are going for a new product, so you obviously know that if you are not only molding, sometimes some machining operations, you need to design your jig or fixtures for that particular product, right? In some cases. So that is also not needed here, because you are not using any tool or any jigs and fixtures. Nothing is there in that. In that, only one nozzle or maybe one table will be there. You can deposit your material. You can add the material one by one over the other. Okay, and reduce development cost, because if you buy the machine and buy the software, it is okay with you because there is no further investment in that. And one disadvantage is some of the machines are laser system, that is maintenance is very expensive, and that machine itself is expensive. That total, the machine is actually expensive. Only FDM technology, FFF technology is actually available with low cost. But if you're going for metal printing, that is selective laser sintering, electron beam melting, direct energy lens, etc., that cost is somewhat higher, because near to 1 crore is the normal price for a better machine. Okay, and another thing is variety of material is limited, because you can't use every material in your additive manufacturing process. So that is one disadvantage. And post-production steps, most of the process, because sometimes you need to go for conventional manufacturing, conventional machining operations to increase your surface finish. Okay, and build size is very limited, as I told you, because if your product have larger size, obviously your available machine may not be fit with that, so you have to go for conventional manufacturing process. And another disadvantage for some of the machines are fume will be created, especially for polyjet technology, what I told you, object 260 Connex. There will be some fume created in that, and normally these machines will be in the AC room, so you need some ventilation part, or maybe some smoke pipe should be installed through that. Still, there will be some irritation for you as you are staying in the AC room with these fumes. That will be one problem with this type of machines. Not every machine, some of the machines. Okay, and applications, as I told you, the food, construction, etc., etc., and patterns for casting. So you can create patterns and you can go for final. That means that pattern, that additive manufacturing pattern, can be used for casting the final product. That is also possible. Functional prototypes, proof of concept. That means you can show your design to the management or maybe manufacturing team for getting further feedback, and you can redesign it. Okay, so as the marketing, or if you're considering the additive manufacturing industry as a whole, so Waller's report is one of the authenticate reports, and that is run by Terry Wallace. So normally they are predicting around 7.5% expansion for this industry by 2020, and they're expecting that it will still go further. And one more thing, due to pandemic, there was some hindrances for, I think except our sanitizer mask, this type of, apart from these type of industries, vaccination, vaccines, I think almost every manufacturing industry is actually badly hit by this pandemic, right? But still it is actually increasing, but the production is actually slightly reduced, or the development is actually slightly reduced due to the pandemic. Okay, and you can see that how this production of AM parts, that is additive manufactured parts, from 94 to 2020, you can see that you can continuously increase is there, especially after from 2012, because in 2002 there is slightly decreasing, it is the decreasing tendency, but after 2012 you can see that its growth is tremendous, right? So when I am coming to our my case studies, that means I will present my research experiences. Before, you should know that what is customization and what is ergonomics. Okay, I hope you heard about these words. Customization, that is actually the action of modifying something to suit a particular individual or task, or maybe a group of individuals. Okay, so customization may not be for an individual customer, but sometimes it may be a group of customer. For a particular ethnicity, you can create or you can produce the product. That means you just say that for Kannur, or maybe for Coimbatore, or for maybe a Kottayam district, the people's some similarity will be there for their interest, some similarities. So based on that, you can create a product and you can sell that. So but the same product will not be sell in Kannur. So that is the difference. So that is actually called as customization. This is a very simple example. Then personalization is normally individual customization. That means you are designing for an individual customer, a particular customer, not for a group of customer. And there are different types of customization is there: transparent, collaborative, cosmetic, additive. I'm not going much in that. We will come to our research part. Okay, so modularization is there. And when you are going to customize it, when you are going to customize a product, obviously you need to get some data or get some information from your customer, right? So that then only you can design according to their needs. So these are some of the customer inputs you can collect. One is functional requirements, how the product should work. So if you take the example of a car, so you know that what is the main function of that. It should run and should carry the passengers, right? So that type of functional requirements you can collect from customers. And if the customer is a very common man, so they may not be very much interested in this type of functional etc requirements, but they will be more interested in these type of things, this emotional as well as aesthetic requirements. So, and one more thing, this is the two difficult terms that we can define. So because emotional requirements, it is very difficult to quantify, right? And as well as aesthetic. But aesthetic in some way or other you can do that, because they may, in one customer may think that red color car will be a better option, but for another customer it may be white colored car. So that those type of things can be actually incorporated in that, because painting a red color as well as a white color for two different cars, it is not a big deal for us. But emotional requirements, it's very difficult to quantify. That is actually a quality one. Then environmental requirements, you know that some of recent products, you can see that recycle, reuse, those type of things will be there, right? So that you can incorporate. That also you can collect from that what actually they need, what the problem they are facing, the customer is facing when disposing the products after the usage. And ergonomic requirements, that is actually the comfort of the users. So when you are designing it ergonomically, so that will be more comfortable for that particular customer. So for example, if you are designing a chair for you, okay, so you have to measure the sitting height, you have to measure your body width, etc. And based on that you can, and by comparing to the table where you are going to sit along with the table, that means you just think that you are going to work in a laptop. So normally you see that you have to sit in the straighter position, your elbow should be supported on the table or maybe some other things. And when you are using mouse, it shouldn't actually, you may experience that. So when you are using your mouse, just think that you are, apart from the wrist to the hand, other all this other all arm part are actually just think that it is hanging outside the table. So after half an hour or 1 hour, obviously you will get some pain in the shoulder as well as elbow, your arm, and your wrist. Your everything will be pained. It will be that is one reason. So those actually you can and ergonomic requirements you can actually design ergonomically, or maybe you can do the work ergonomically. Both are there. Okay, so just think that if you are going to nail, you are going to hit a by using a hammer, you are going to pierce a nail in the floor or wall. Okay, at that time, so you need some height, right? So at that time, if you are just nailing it uh, above your head, that means at that time your hands are very much high, so your pain will be more. So instead, you can what you can do is you can place a stool or something on that, and you can always try to keep your hands, arms nearer to your body. So if it is away from your body, that is not ergonomical. So always keep your arms etc nearer to your body, that will be more comfortable for you. So this actually you can do some of the work ergonomically. And another example is when you are lifting some weight from the floor, so don't bend your, that means when at the waist you just bend it and you usually pick the weight, right? I hope you experience that. So there is a chance of getting some pain on your waist as well as your backbone, but don't do that. You sit there. Okay, you sit there along with your weight should be carried. So then lift it some height, then you stand up, then you can walk away. So that is one way to do the things ergonomically. So otherwise it will be very difficult for you. That means sometimes it will happen, your waist or something will be twisted, so you will get, and that means 1 week pain will be there, right? So that is one thing. So you can do some of the things ergonomically, and you can design some of the objects ergonomically to suit with your that means which will be suitable for the customer. And next one is actually user fit requirements. That is actually along with this is actually customization. And customization ergonomics is actually, it is two sides of a coin. So standalone with this customization only, it will not be good. So you can merge this, or you can combine these ergonomic factors as well as customization factors together, and actually you can do the design. So that will be better for you, or better. So you can see that here, this sitting on a working on a computer. So this is actually the ergonomic factors. You have to think about the height, sitting height, as well as your width of the body, etc. You can see that this particular handle actually designed according to the shape of this one. So it will fit this hand very perfectly. So it will be easy for him to use that particular product. Okay, so this is the basic idea about ergonomics as well as customization. So actually my topic of I hope you remember that my topic is actually user involved product development, right? So in everything you have to, if it is possible to bring the customer in every stage of your design process, that will be better for you. And that you can think about, or obviously you can produce a better product for that customers. Okay, so try to involve the customers in your design stage, every possible stage. Okay, so that's what the idea behind my research. Okay, so when I started my research, my guide told that, so Sreekanth, our hand size is actually different, right? So did you ever come across this? You think about this, our hand size is very different, right? Even though if you are from same ethnicity, like South India, or maybe North India, or maybe Kannur, Kerala, or if you even if you think about that, still our hand size, our body dimensions are very different, right? So collecting these body dimensions is actually called as anthropometry. Hope you understand that. Anthropometry is anthropology. You may have heard about that, right? That is actually studying humans, studying about humans, Neanderthal, Homo sapiens, etc. Right? But anthropometry, that metry is actually the measurement. So this is actually measuring the body size of a particular customer and design the product for that particular customer. And depending on the product, so this body dimensions will be different. That means you want to collect for a handle. If you are just designing a handle, you need to collect hand dimensions, not the body dimensions like sitting height, etc. But if you're designing a chair, obviously you need to measure the sitting height as well as the width of your body, right? So that is a that means depending on the product you need to design, or you need to change you need to collect the anthropometric dimensions accordingly. So that actually depends, or that actually will say that which product actually you are designing. So based on that you have to collect the anthropometric dimensions. Okay, so in that when this research came, actually our idea is to design a product for the in the healthcare sectors. So in healthcare sector, actually we need to design a product. So we need to select a product from healthcare to customize it and to make the customers more comfortable. Okay, so you can see that in healthcare there are hospitals, pharmaceuticals, diagnostics, medical equipment and supplies, medical insurance are there. So obviously by analyzing these hospitals, that is government, private, etc. So we don't much have to do in that. Pharmaceuticals, that is different, that they are creating, they are generating medicines, right? So an engineer can't do anything. And diagnostics, obviously laboratories, they are doing the testing, all those things. Still the machines are there, the customization is not that much involved in that. And especially medical insurance, so there also customized medical insurance will be there, but that is not a job of engineer, right? So that is different job. So but in medical equipment and supplies, obviously there are a lot of instruments are there, right, used by different type of people in the hospitals, that is surgeons, maybe normal doctors, then pharmacists, different people are there. So when I went through this research literatures, etc. So you can see that there are two types of, because doctors normally have more problem with this. Why? Because they are normally doing the surgery, and they are doing the work for a prolonged time. And especially in doctors, there are surgeons are there, non-surgeons are there. Non-surgeons, they will use normally the stethoscope, simple objects. But surgeons, if you are going to analyze what actually surgeons are doing, their surgery, that surgical procedure may be for 1.5, maybe 7 to 8 hours for something. Otherwise 1 hour, 2 hours, it's normal, right? So, and it is actually precision work, very precision work. If anything happen, that means any simple error can cause a man lost his life, right? So it's a risky job as well as a prolonged time is actually needed in that. So at that time, you have that surgeons have to be more cautious about what actually he or she is doing, right? So they're actually in a difficult situation when they are doing the surgery. And in that, especially in the laparoscopic surgical, so open surgery, obviously you know that when you are doing the open surgery, you will open the body part and you touch the organs directly. The surgeons will touch the organs directly, and there is no much problem with that. But if it is in a laparoscopic surgery or minimally invasive surgery or keyhole surgery, there is a problem with the surgeons that they are actually inserting some of the tools by creating a small hole in the body, and they are inserting this camera, light, other tools, okay, uh, inside the body, and they are projecting that surgical area to a monitor. So when the surgeon is doing the operation, so when he is moving that tool to the right sides, it may have there is a chance for it that inside the body, that tool is moving in the other direction or maybe in the same direction. So he should be conscious about that. So because of this consciousness, they are actually their prolonged surgical time actually leads them to an discomfortable stage, and they are getting pain throughout the neck, arm, through to the hand. Okay, so and it leads to surgical errors. So surgical errors, what is actually because of the surgery, you are creating some injury to the patient, or ultimately that patient need to stay in the hospital for more days, and it followed by some other, and that means some other surgeries also. So it is actually a, for that what we thought about, if we are designing a hand tool, okay, for that particular surgeon with his particular hand dimensions, that will probably, and we will incorporate some of the ergonomic factors in that. So obviously that comfort level will be increased for that particular surgeon, and obviously we can reduce these surgical errors. That's what the idea behind our work. So you can see that this is open surgery and this is laparoscopic surgery. Okay, so based on that, what I did is I went through a survey among the surgeons in and around Coimbatore, as well as through some mail also, email also. So I collected some of the email from surgeons and I sent the my wish and what my objective to, related to my research. And some of them replied, some of them not replied, obviously. And I met some of the surgeons personally, so I collected some of the data. Okay, so based on that, what I concluded that they are having a problem in hand, especially, and with forceps. So based on that research, based on that survey, I decided that based on a hand size, we will design or we will redesign a forceps handle. Okay, so these are the dimensions actually I collected. This is total hand length, distance, palm length, palm width, as well as the circumference of the fingers. Okay, so I'll tell you, and some of the time we may not be able need to do all these dimensions or incorporate all these dimensions, but as it is hand, I started with collecting the data, and at that time actually I didn't get my that means which forceps I've been actually selected forceps, but we didn't have a design or existing design, we didn't get that. So we don't know what actually the dimensions we need to incorporate. So as you know that if it is a PhD research, we can't wait for something for a long time. So we have to do some of the other things parallelly, right? So obviously we know that main dimensions for a hand is these are the dimensions. So what I thought is we will collect the dimensions first. Okay, so when we got the existing product, we will analyze that and we will identify what are the critical dimensions we need to incorporate in this, then we will redesign it. Okay, so that's what the idea behind it. So we started collecting the data and we collected around 280. That means I collected around 280, and obviously I got some help from our students as well as my fellow researchers. And I collected in and around Coimbatore mainly, and something mainly Coimbatore region, because that's what more comfortable for me to reach these subjects, right? So and so these are the data, descriptive data I collected, and I conducted a pilot study whether the dimensions is actually within the limit. Okay, so based on that, so this is actually how we are going to orient it. Okay, so in that, so that study actually I did. Last one, we got an object or existing forceps design from Hospins. So this is a surgical tool manufacturing company that is based in Coimbatore itself. So fortunately we got one design from him. Okay, so we started analyzing it. So these are the two machines we used. Okay, so we printed accordingly, and actually we prototyped 3 designs. Okay, we prototyped 3 designs. That is, first preliminary design we just went through. Okay, how it will look like and what will be the problem. So one was the problem with this is we used a shell structure inside that, so it will be actually void space will be there inside, so strength is very less, so we have to increase the strength. That's what one. And this height is actually slightly more, and the surgeons are not able to reach this thumb, so that actually we need to, that dimensions we need to reduce. So according to the dimensions. Okay, so and another one was, this is actually another user comfort module we incorporated in this modified design. So because you see that here there is no such things, right, in the existing design, but here we incorporated that for supporting. That means you can increase the contact area. I will show you that how it is actually increasing the contact area. But this actually at that time we did, for the first design we didn't consider the palm width of our hand, so it is actually piercing. And for a long time, if it is hitting on your hand, inside your hand, so obviously there will be some pain on that. So we have to increase the length of that according to our palm length. So this was the basic idea or basic analysis based on the first design. So we redesign it. You can see that we increase the length of that user comfort module, and later on, so this is actually based on minimum, median, and maximum dimensions of the data we collected, hand data we collected. Okay, you can see that based on this actually. So this is age, height, weight, BMI, shirt size, C1, this circumferences, and total hand length, distance, palm length, palm width. Okay, so based on this actually we design 3 designs. Okay, for minimum dimensions, maximum dimensions, as well as median dimensions. But we actually need an individually customized product, right? But this is not actually individual customized. This is actually designed for one particular group. That means the group will have a minimum hand dimensions. So what we did is we have a base model, right? So this black part is actually the base model, and what we did is according to the dimension we redesigned or we designed a rubber insert in that, because I already told you that polyjet technology, this object 260 convex machine, have a advantage of printing rubber like material. So if you are inserting a rubber insert, so that rubber insert, if you insert that, that will be, so if this is maximum dimensions, if you insert minimum rubber insert, so that at that time that will be suitable for the people with hand dimensions minimum. Okay, and one more thing, so if you have a model like this, okay, it is already there in your system, computer system, right? Or maybe in your cloud. So you can bring that, and if a customer is coming for you to have a surgical tool handle according to his hand size, what you can do, okay, you already know that what are the critical dimensions, the diameter or circumference of this hands, because here this hand the fingers will be there, a little finger, middle, as well as little, ring, and middle, as well as the thumb finger. So point finger, that point finger should be there to operate this part. So that will always, because here there is a rotating part, because here this is actually using for holding the holding the organs inside. Okay, so you have to, by operating this will close and open. So this part will close and open. So at that time sometimes you may need to rotate this. So this is actually the rotating, there is a rotatable appliers is there. Okay, rotatable appliers is there. So you have to rotate by using your point finger. So that's what the point finger should be always outside this part. So by using that thumb point finger, you can rotate that. Okay, so that particular surgeon is coming to you, and you have this base model. What will happen? So if his dimensions is below this maximum dimension or your base model, what you can do, you can just print this rubber insert, 2 rubber inserts according to his hand size. You can just, because rubber inserts is also there in your CAD computer environment or virtual world. So at that time what you can do, you can just redesign the dimension or rearrange the dimension, that you can directly print in the machine, and you can insert that, and this base product also you can take print out, because that is also not available physically, right? Only in the virtual environment it is available. So you can print all these things. Maybe it may took around 6 hours, because you can see that this actually took 4 hours approximately, or maybe it may be 6 hours to 7 hours. So obviously the design as well as the prototyping stage will be long, maybe maximum 1 day. So within 1 day you can send the product, final product to the customer. Okay, so this is the printed parts of that, and this is actually maximum dimension, and we, for a testing purpose, we actually, or for analyzing purpose, we actually print it for minimum as well as median dimensions. Okay, minimum as well as median dimensions. So that will be completed. Okay, so you can see that this is the finger positions. Okay, this is thumb, little, ring, middle, and index finger. That was the existing, and this is the modified design, and here that thumb will come, and this will be move up and down. So because of that movement, what will happen, this forceps will be open and close according to your quantum movement that you can operate, and point finger will operate the rotatable applier. Okay, and you can see that the existing design, only the contact area is this much, but for modified design, it is actually increased because of that user comfort module. So obviously, if you are increasing the contact area, you can take up the load perfectly, right? So that will actually increase the comfort, and this is actually piercing effect that is reduced, or it's almost eliminated. Now this is actually in this wrist position. That is another ergonomic factor we incorporated. That is, this wrist position is actually twisted position in the existing design, but this is more in a neutral position or straighter position. That will also increase the comfort. Okay, so some analysis for the thesis. Actually, this is actually done for thesis, for a stress analysis, how much load is actually taking up. That for that we actually applied a 97.13 Newton. That is a grip force, normal grip force for Indian males. So that we applied, and we got that it is almost, that material is almost okay, but it is not final. That is the prototype, because final design, if you want to commercialize it or market it, obviously you need to do a lot of other things, that taking permission from IMA, that type of boards, you need to take permission to test that particular tool in a patient. So that is a lot of process there. For completing the PhD, I actually did up to that, and I, by showing the existing as well as the modified design to the surgeons, around 80 surgeons I met personally, and I collected the data from them. So obviously they are saying that because functionality, that is actually a relative term, because it's a prototype, they can't test that. So that's what it is actually coming 3.61. They are actually not able to understand that what is actually how it's function actually, but they're telling that it is grip strength as well as comfort and wrist posture. With this, actually they are very much satisfied, but functionality they were not able to tell that, because they have to do the operation with that tool, then only they can tell that. Okay, so that's what the, so this actually I combined these three areas, that is customization, ergonomics, anthropometry, into a healthcare product to manufacture through additive manufacturing. Okay, that is actually possible. So case study 2, this is actually my UG project, recent project, very recently we completed, but due to pandemic we are not reached the expected position in this particular project. But still, the strategy I already told you in this previous session, right? Previous case study. Similar strategy we actually applied here, but for not for the healthcare product, but for a handmill. Okay, handloom industry. We actually went to a handloom industry nearby. I hope you know that Kannur is famous for handloom industries, right? There is a legacy for that. So we went to a handloom industry and we talked with them. Actually, my students did that because that was their project. They talk, and this is a winding machine. Okay, so this is actually made by wood. Okay, they have to rotate this one, so they have to wind the string or that in the machine. So for that, actually, they are doing this operation. But mostly females are using this particular machine. So it's actually hand machine. So they are rotating this part. Okay. So for that, actually, because it is holding in this position, so we need grip diameter. Okay, so normally this is called as grip diameter, and total hand length, palm length, and palm width for designing. So we collected from around 65 workers, female workers from that industry, and we collected a descriptive statistics, and based on that we designed it. Okay, we designed it according to the dimensions, and this is the CAD model for that. And we used, because as I told you, due to pandemic we were not able to go to some other college or other industry for printing these objects what we designed. But we have a machine, a small machine that is called as FFF machine, that is Flash Forge Dreamer. With that, actually we print it using a PLA material, polylactic acid, and this is what actually I shown you in that video. Okay, so but actually it is a scale model, because that build size is very limited for our available machine, and because of that we actually did a scaled model, and for our project purpose we did that, but it's actually not finished in my view, and we printed according to that. And this is actually scale model. We are not able to test this, or we are not able to get a feedback from the workers, and we were not able to go there because we need to complete that by May. So you know that's during April and May it was almost shuttered down. So we were not able to go there and get the feedback. So instead of that, we just take the printout. But this actually strategy is actually good. We can incorporate that, but we need to go some more distance for completing that project. Okay, and we did a small analysis on that. And for our project purpose, we analyzed it using ANSYS. Okay, so that handle, again, we use that grip strength for analyzing it, and obviously this ergonomics anthropometry customization and additive manufacturing for a hand tool in hand wheels. That is also possible, and that's what we did. Okay, so these are some of the examples from that is actually I went through. That means that's my personal experience I told you in a project and a research. But this is some of the work done by some of the researchers from the hand wheel for wheelchair, handle for wheelchair. So they take the impression. This some other methods you can adopt to design a handle. Okay, so they in a clay this they made this impression of that particular individual's hand, and they scan it using computer tomography data or MRI scan that you can change that a diacom file, and that you can bring to your CATIA or some other similar environment. You can redesign it and you can print that. You can see that the total process to complete this project or complete that handle is actually 15 hours 45 minutes. That is within 1 day. Even 1 day is not enough needed for completing that project. So in that way, you can think about additive manufacturing for redesigning it and customized design. So this is actually a clamping hand tool. So the worker need to hold that work will be fixed here, and that will be holded in the hand, and then he will work that. So this will actually, that worker will be in an awkward position because he's carrying the weight of the work as well as the tool, right? So the researchers think about Shin and Kim, they redesigned it, and according to that means this sharp edges are reduced, the weight is reduced, all those things are they incorporated in the final design. And this is another tool, chisel, they also redesigned, and they used it as a pattern, and they casted it using some material. This is actually the RP model. Okay, and this is the final product. So this is what they did in that. So this is some glimpses or some idea behind how you can incorporate this additive manufacturing as well as customized design in hand tools. Actually, I told about all hand tools, right? Handles, but you can obviously think about some other products, other similar or maybe different products, how you can incorporate this type of ideas into your customized design. So that means this is actually giving you how you can collect the anthropometric data, what are the anthropometric data you can have to collect, and what are the ergonomic parameters you have to incorporate. Those things you will get a basic idea about my talk. That's what actually my aim. You can think about a new product or new entirely different product, and you can think about a customized product using additive manufacturing. Okay, so I actually talk about only this hand tool designs. Okay, obviously thanks to my supervisor, Dr. Rajesh Ranganathan. Without him, obviously it's not possible, and the team, Additive Integrated Manufacturing and Management Research Group at Coimbatore Institute of Technology, and obviously Vimal Jyoti Engineering for that case study too, and my project students. So they actually did almost every work. I just guided them. So because I know that what I did in my PhD, so we just thought about incorporating those similar idea to a hand wheel, means handloom industry hand tool. Okay, that's all. And Kanji Road viewers, they actually helped me. They allowed us to go inside the industry and talk with the workers, etc. And obviously all scientists, engineers, and to you also, because they are all working for making this scientific community in a better stage, right? Better. They're actually growing every day. And obviously the images I used in this presentation is just for information purpose, because I have to tell the courtesy to those people who created those images. Okay, so I thanks one and all the participants present here for listening to my experiences. Okay, so hope it was informative. Okay, so thank you all, and especially thank to Lijo sir and Pradeep sir for inviting me to for a talk. Okay, thank you, thank you.
Yeah, thank you very much, Dr. Sreekanth sir. And we'll have an interaction section, so the participants can unmute and ask questions here now.
Yeah, sure, sir. Thank you.
Yes. I think Ibn Shukur, you can unmute and you can ask the question.
Good afternoon, sir. Sir,
Yeah,
how
yeah.
we can, so after 3D printing a material, so how we can remove the support material from that properly?
That's what I told you. There are different types of, especially in FDM technology, you need to remove the support structures. And as well as in your polyger technology, that means different technology, the different type of methods we are actually using to remove the support material. That's what I told you. There are BAS, breakaway support structures are there, chemically soluble support structures are there. Uh, in BAS, you will actually use some chisels or likewise objects to remove the material by breaking it. Okay. In chemically soluble, you are just putting this model material, that means your product, fully in that hot water with the chemical solution. So that will actually soluble in that material. And in polyjet technology, what I used, Object 260 Connex, there's a water jet machine coming along with that particular machine. Okay, so you can remove the support material by injecting the water jet on it. And water jet, it will be around 230 bar pressure. If I am remembering correctly, it's around 230 bar pressure. That much pressure will be there in that water. It's actually a jet, it's high, very intensified jet. So that will remove the material. So, and for in SLS, selective laser sintering, etc., there sometimes may not be needed as support structures, because that powder, uncured powder, because you are in some cases that is selective laser sintering, you are actually feeding the powder on a table. Okay, so that only that powder will be cured wherever it is necessary. Okay, so that uncured powder can support this object. So that's what happening in selective laser sintering. Sometimes for better removal, so they are actually creating some support structures, but that will be break and they will use the object. So that's what actually happening. That depends on which machine you are using and which type of that means that particular that industry or that manufacturer will tell you how you can remove the support material. Uh, are you satisfied, Abin, sir?
Yes, okay, sir. Thank you. Thank you. Thank you very much.
Yeah, thank you. Thank you, Abin, sir.
Yeah, any more questions?
Sir,
Yeah, please, sir.
actually, I have got a question. What are all the challenges that we might face, especially in doing research works on research work based on in vivo biomedical applications with respect to additive manufacturing?
Pradeep, sir, I don't have any experience in this in vivo projects,
Yes. Yeah, yeah.
but I can tell you what I experienced, what are the difficulties I experienced when I am designing this particular surgical handle, okay, for
Yes.
surgeons. So that I will share with you because I don't know what is this. That means I didn't have any experience with this in vivo biomedical applications, but in my research, what actually I experienced is, one is the availability of the resources. Okay, because one thing is, if you want to make the final product, we need a good machine, and that is costly. That is one thing. So I am compelled to go for a prototyping one, because I have to complete the PhD within this stipulated time, because you know that in PhD we have a time frame. But if you are in a research, that means there is no time frame. Obviously you can check different aspects of this methods, as well as the materials or maybe manufacturing process, anything you can check. But in PhD and obviously there's if even if you are getting a funding, obviously you know that there is a time frame for that. Maybe they may give only for 2 years or 3 years, right? Within that you have to complete that. So that time is actually one problem in research. And another one, in while collecting the data, that is for this how which tool actually the surgeons are getting more pain, discomfort, etc. When I am doing that survey, when I contacted some of the surgeons or doctors, at that time they will tell one thing: you are not from our area. That means they didn't know that actually this type of instruments actually designed by engineers, but they are actually using it. They are the end users, but actually designed by engineer, but they won't understand that actually. Some of the surgeons, okay, not everybody. So most of them, 90% were actually cooperative, but some of the surgeons may not. And one more thing, they are busy people. They won't reply in time, because you know that we have a time frame every time. So they won't reply that. We have to keep on sending the reminders, and that will be annoying them. That will be actually awkward for them. So keep on sending the emails, or maybe keep on contacting them through our phone, or maybe by meeting personally. Because I will tell you that when I'm going for this survey for both stages, that means preliminary stage as well as the subjective rating stage, the final stage, sometimes you may need to wait from 9 to 5 for meeting one surgeon. That's what the thing. So you will go, because the superintendent may be given time to reach the 9 o'clock. So I have to reach at 9 o'clock. But the surgeons, these doctors may be always keep on contact. That means patients will be in line. So obviously they will give preference to patients, not for us, because we are actually in the different area, right? So that's what another problem. So we have to wait for 8 hours or 9 hours to meet at least one. So I almost spent around 4 to 4.5 months, or maybe more than that, to get enough. That means only 80 I got that. 80 surgeons I got the final feedback. But in the preliminary stage, actually I used email also, because this final stage I have to show that means I have to bring this existing as well as the final design to that particular surgeon. He has to use, or you have to keep that in his hand, both, and he has to tell that, okay, how it feels. So for that, email survey is not at all possible. But in the preliminary stage, email survey was there. So I got some 60 to 70 emails from different people. So that's what actually, that's what one advantage in that. But in subjective rating, I have to meet all these surgeons. So that's what one problem. And obviously, you know that some designing, that type of parts, because we may not be a very, because we have to get help from some of the experts in that modeling thing, because everybody will not be an expert in that modeling. We may know that how we can do that, but some things we need to get help from others. So obviously you need to get help from others. So these are some of the problems I faced in this. And obviously in additive manufacturing, especially in this type of areas, very limited research are going on. Especially in a lot of research is there, but because I actually need to test in using an electromyography analysis, because that will actually give you the muscle contraction, muscle strain, okay, by using existing as well as the final design. But I searched a lot of in and around Coimbatore, and only one was available in PhD Tech, but that machine was used for bigger muscles, not for small muscles in hand. That was not possible. So I have to skip that stage. So that's what one a problem, or maybe one limitation in my research, actually, in my PhD research. Is that okay, Pradeep sir?
That means we need to face a lot more challenges.
Yeah, there are a lot of challenges in this, especially because if you want to go for a metal additive manufacturing research, the minimum cost is, as far as I know, it is around 50 lakhs to 1 crore. Normal machine. And another problem in that, only in beta version you can get this, you can test the materials. But all normal machines, you have to go for the materials what the particular manufacturer is saying. You can test a new material in that. So material research is actually one good area in additive manufacturing, but because you know that in powder technology, sometimes if it is not correct combination, there's a chance for explosion. I think that you know that, because this powder have a problem with that. So if that should be considered in that. So when you are going for a new material research, at that time, obviously, you have to go for a beta version. That is, I think minimum cost is around 2 crores, if I am correct. Is that okay, sir, Pradeep sir?
Yes, sir. Thanks.
Yeah, there are a lot of challenges. We have to eradicate a lot of things in that.
Sure. Any more
And
questions?
getting funding also, it's I think slightly difficult nowadays, because I submitted for a funding in CRD for this particular project, UG project, but I didn't get that. And at that time itself, I hope you remember John sir. He was the principal of Kannur Engineering College. I don't know if you know him. He was the dean research at that time. He told that Sreekanth, it will be very difficult to get at this time because pandemic and limited funding. That is another problem for us. Yeah. Thank you, sir. Thank you, Pradeep, sir. Okay. Okay. Thank you, participants, to all of you for patient listening.
Sure.
And thank you, Lijo sir and Pradeep sir.
Sure. Can you once again we thank you, Dr. Sreekanth sir, for a very informative session that was taken in the second session. And I hope all the participants have received a very good informative, especially with the case studies that he has explained and what are the challenges he has faced while doing the research and getting the funding and everything. So I hope the entire session was really informative, and I hope some of you will be taking the positive sides and positive strokes from these sessions. And yeah, I think one more. Oh yeah, no questions. Okay. So once again, we thank you, sir, for joining with us. Thank you very much.
Thank you, sir.
Okay.
Thank you. Thank you all.